Hello everyone, this is Ashoke, your personal guide and mentor. I welcome everyone to my YouTube channel AKB Tutorials. Here we are going to discuss and cover some important concepts of mechanical engineering that are very useful and helpful for competitive exam and job interviews. So let us start today's session. Hello everyone, welcome back to my channel AKB Tutorials. I am Ashoke from AKB Tutorial. Today we are going to discuss one of the most important topic of strength of material, that is thermal stress strain. So in this topic, first we will see the general behavior. So general behavior is whenever a body is heated, say a body of length L is given, and if the body is heated by some temperature, so if this body is heated with a flame to some temperature, say the increase in temperature is delta T. So what will happen? The body will extend in size. So that means some deformation will take place in the body because of the temperature difference. So because of this temperature increase, the elongation of the body, say it is given by dl, then dl is given by dl is equal to L, original length of the body, into alpha into delta T. What is alpha? Is thermal expansion coefficient, and delta T is the rise in temperature. So L into alpha into delta T is the deformation produced because of this temperature difference delta T. Now the strain developed in the body, that is called thermal strain, developed in the body is equal to, say, epsilon, it is equal to dl by original length. What is dl? L into alpha into delta T. So L into alpha into delta T by L, that is equal to alpha into delta T. That is the thermal strain produced in the body. Now if the end is not restricted, ends are not restricted, then the stress developed in the body will be 0. If the end is restricted, okay, if the end is restricted, or in other words we can say if the support is rigid, if the supports are rigid, then only the stress will develop in the bar, okay. Or in other words we can say the support will compress the member by dl amount, thereby a compressive stress will develop in the bar. So the kind of stress developed in the bar, if the temperature is raised, is compressive stress. I hope it is clear, and we will find what is the stress developed in the bar. So we have got the strain value, that is alpha into delta T. Now say stress value we will obtain from that Hooke's law. So Hooke's law says sigma by epsilon is equal to Young's modulus of elasticity, or sigma is equal to E into epsilon. Now what is E? Okay, E is the Young's modulus of elasticity and epsilon is the strain produced in the bar, that is alpha into delta T. So we can find sigma as E into alpha into delta T. So we will take the cases one by one and we will see. So there are cases. First case we will see, that is when the support is fully rigid. So when the first case is case 1, that is when the support is fully rigid, is fully rigid. If the support is fully rigid, say this is the bar. Bar is supported between these supports, that is two end supports, and these supports are rigid. Original length of the bar is L. Now, as the temperature is raised, if it is raised, then some deformation will produce in the bar, and it depends on the rise in temperature or fall in temperature. Okay, so consider the rise in temperature is given as delta T. Now, the expansion of the bar is given by delta L is equal to L into alpha. Alpha is the thermal expansion coefficient of the material of the bar, and into delta T, that is either rise in temperature or fall in temperature. So if rise in temperature is taken place, then the expansion of the bar will take place. If the temperature is decreased, then the bar will contract. So when temperature is raised, so that time the stress developed is compressive stress, and when the temperature is lowered, then the stress developed is tensile stress. So now the strain developed or thermal strain produced in the bar is given by delta L by L, that is change in length to original length, and is given by L alpha into delta T by L, and that is equal to alpha into delta T. And the stress developed is obtained by the Hooke's law. So stress by strain, as per Hooke's law, within elastic limits, stress by strain is equal to a constant and is known as Young's modulus of elasticity. Thereby sigma, that is stress developed in the bar, is equal to E into epsilon. So E into epsilon. So by replacing this epsilon, so we can write E into alpha into delta T. So that is the stress or thermal stress developed in the body, and alpha into delta T is the strain developed in the body. So this is about the first case. Now we will see the second case, when the support is not fully rigid. When the support is not fully rigid. So this is the second case. So there will be some deformation produced in the support. So, or in other words, support shifts when there is a stress developed in the bar. Okay, so now let's see. The bar is under two supports. The supports are not fully rigid. Though that means, so there may be some deformation produced in the supports. So now, this is the left support and this is the right support. Okay. Whenever this bar is heated to some temperature, bar will expand in size. Say this mass is the expansion. This is called free expansion. So that expansion, if it is given by delta L will be equal to L into alpha into delta T. Say delta T is the temperature difference produced in the bar. So L is the original length of the bar, alpha is the thermal expansion coefficient of the bar material, and delta T is the temperature difference. So the free expansion of the bar will be delta L. But if the support shifts by some amount, say due to this the support is shifted by some amount, say this amount is given by delta amount, it is shifted. So once the support is shifted by delta amount, in other words we can say the support restricts this expansion, or this expansion is compressed by the support. Okay, so that expansion, or we can say effective contraction of the member, is given by, that is delta L minus delta is the effective compression. Effective compression. So effective compression of the member is given by delta L minus delta, and the original length of the member we know as L. So thermal strain developed in the bar, thermal strain developed is given by epsilon is equal to delta L minus delta divided by L, where delta L is given by L into alpha into delta T minus delta divided by L. This is the thermal strain developed in the body. Okay, L is the original length of the bar, alpha is the thermal expansion coefficient of the member, delta T is the temperature difference created, and delta is the amount by which the support is shifted, and L is the original length of the bar. So we have got the thermal strain. Now what is thermal stress developed? So thermal stress is equal to, say it is given by sigma and often by using Hooke's law is equal to E into epsilon. So E is a constant that is known as Young's modulus of elasticity, and epsilon is given by L into alpha into delta T minus delta divided by L. So this is the thermal stress developed in the bar when the support is not fully rigid, or in other words support is shifted by delta amount when temperature is raised by delta T, and this is the thermal strain developed in the member, that is L alpha into delta T minus delta by L. Now we will see the third case, that is a bimetallic strip. So what is the stress and strain developed in a bimetallic strip? Let a bimetallic strip, it is made of two materials, say copper and steel. So consider a bimetallic strip, say this is the bimetallic strip, or two plates are rigidly fixed at the ends, and say top one is the top two metal pieces are fixed at the ends, and the say top one is made of steel and the bottom one is made of say copper. So this bimetallic strip is made of steel and copper. So this bar is made of steel and copper. Now initially consider that there is no restraint and the bar is heated to some temperature, or say the temperature difference created here is delta T by a by a flame. So with the help of this flame, the temperature difference is created to delta T. Now, because of delta T and there is no restraint, both the bar are of length L. So original length of both the bars, say it is L. And because of this, both the bar, there will be free expansion on both the bar. So diagrammatically, if we see, say after the increase of temperature to delta T, say the bar will increase. So let this one is the original length, that is given as L. L is the original length of the bar, and the free expansion of steel bar, that is the free expansion of steel bar, free expansion of steel bar. This is made of steel and this is made of copper, and this much is the free expansion of copper bar. Free expansion. So we have got the free expansion of steel bar and free expansion of copper bar. Now free expansion of that steel bar is given by L into alpha steel into delta T, because delta T is the temperature difference created. So once the temperature difference is created as delta T, so L into alpha steel into delta T will be the free expansion of steel bar. And if we see the free expansion of copper bar is given by L into alpha copper into delta T. This is the free expansion takes place because of the difference of delta T is created. Now, if the ends are rigidly fixed, so that means the expansion and compression will take place altogether. So that means, so if we see in another figure, okay, say first one, this is the original length of the member, and this is the free expansion, this portion is the free expansion of steel, and this portion is the free expansion of copper bar. So this is the original length, each L is here, okay, and this one is the free expansion of steel bar, and this much is the free expansion of copper bar, because the alpha value of copper is more, so the free expansion of copper bar will be more than that of the steel bar. Now, as the ends are rigidly fixed, means ends are fixed, so that means the increase or compression will take place simultaneously. So thereby there will be a force developed, and due to that there will be a common deformation produced in both the bar. So this is the common deformation produced in the bar. This is the common deformation. Common deformation. So what is the value of this common deformation? So common deformation on steel bar as well as copper bar, it will be same. Now due to this, the steel bar will increase more by this amount and copper bar will depressed by this amount. So because of this, there is a force developed in the bars. So that bar, say P is the force developed in the steel bar, and same amount of force developed in the copper bar, that is, say, this one. So thereby P is tensile for steel bar, thereby the steel bar is extended extra by this amount, and P applied on copper bar is compressive in nature, thereby it will compress by this much amount. So in other words, we can say the nature of stress produced in the steel bar is tensile stress, and the nature of stress developed in the bar is copper bar is compressive stress. Now the common deformation for both the bar will be same. So thereby we can write common deformation of steel bar, and that will be given by, first one is the free deformation or free expansion, then the deformation produced due to force P, that is free expansion plus expansion due to force P. So common deformation for steel bar, if we see, that will be the sum of free expansion plus expansion due to force P, because force P is the tensile force acting on steel bar. Similarly, if we see the common deformation of copper bar, now the common deformation of copper bar is given by, that is the free expansion minus this much, that is the deformation due to force P, that is free expansion minus deformation produced or expansion produced due to force P. So now let us say free expansion of steel bar, that is L into alpha S into delta T, that is the free expansion of steel bar, plus expansion of steel bar due to force P. So we can write P into L original length by A into E steel, area steel, and that will be equal to the free expansion produced in copper bar, that is L into alpha copper into delta T minus the compression due to force P, that is P into L by A copper into E copper. Okay. So this is the formula by which we can calculate all the requirements of the questions. So this is the most complicated case, that is thermal expansion of a bimetallic string. The ends are restricted, so thereby this is the first case which shows the original length of the bar. When the bar is heated, the free expansion will take place. We are considering there is no restriction against the free expansion, thereby steel bar will expand a small amount, and the copper bar, because of alpha value is more, so copper bar will expand more. Now the free expansion is calculated L alpha is T into delta T, and for steel bar L into alpha Cu into delta T. Now if the restriction is applied, means ends are rigid, so thereby a intermediate force will develop in these two bar. That force will be equal on both the bars, that is P. Say P is the unknown force is developed. Because of this force, this extra expansion on steel bar will take place because of load P produced in the bar, and the compression of this much on copper bar will take place because of that load P developed. Okay, so the common deformation, so this one is the common deformation of steel bar is given by free expansion plus expansion due to force, because you can see easily this is the free expansion and this is the expansion because of load P produced inside the bar, and that will be equal to free expansion of copper bar minus the compression produced by load P, okay, produced in the bar. And mathematically we can write L alpha delta T is equal to P into L by AS into ES, so is equal to L into alpha copper into delta T minus P into L by A copper into E copper. So this is all about your bimetallic strip, where L is the original length, alpha S is the thermal expansion coefficient of steel bar, delta T is the temperature difference created, P is the load developed in both the bars, that will be equal, L is equal to the original length of both the bar is equal L, and AS. So we can again reduce this formula, that is L into alpha S steel into delta T plus P by AS is sigma S, that is stress developed in steel bar into L by ES, and that will be equal to L into alpha copper into delta T minus P by A copper, this is the sigma copper, that is stress developed in copper bar into L by E C U copper. So this is the formula we can use for solving the problem. And one more thing, when the bar is heated, the kind of stress developed in these two bar, so steel bar whose coefficient of expansion is less, so on that the tensile stress will develop, and the copper bar whose coefficient of expansion, thermal coefficient of expansion is more, in that the compressive stress will develop. So these 2 points you have to remember. Now we will see one more case, that is thermal stress in a taper bar. Thermal stress in a taper bar. So earlier we have studied the deformation of a taper bar. So we know what is a taper. So if we see a taper bar, so this is seen like this, a gradually increasing or decreasing bar is called a taper bar. Now say small d is the diameter, say we are considering a circular taper, small d is the diameter at this end, at right end, and at left end it is a capital D. So the diameter at both the ends is given by small d and capital D. Okay, and say L is the length of the bar. So L is the length of the bar, and one end the diameter is capital D and other end diameter is small d. Now say this bar is fixed by two end supports. Okay. If the bar is heated, say with the help of a flame, if this bar is heated to some temperature, say delta T is the temperature difference created here. So because of this temperature difference, the bar will expand, and the expansion is given by, say, delta L is given by L into alpha into delta T. So delta L is the deformation produced in the taper bar, say. So this is the deformation produced in this bar. So this one is your delta L. So delta L produced in the bar is given by L into alpha into delta T. Okay. Now, as the supports are rigid, what will happen? So because of the supports are rigid, so it will not allow the bar to expand. So thereby a compressive stress will develop in the bar. Or in other words, we can say the support will compress this delta L amount. So thereby stress will develop in the bar, and the kind of stress developed will be compressive stress. So now, so we have got this delta L. So strain as well as stress we can find easily. So delta L is the, so we have seen the deformation in the bar because of temperature rise, delta T is given by L into alpha into delta T. So in earlier case we have seen in normal, when P load is applied over the member, say P is the load applied over the member, the deformation produced in this taper bar is calculated as delta L is equal to 4 P L by pi E into small d into capital D. So delta L produced in the member is given by 4 PL by pi E into small d into capital D. So now if we equate these two delta L, so we can find what is the load developed in the bar or thermal load developed in the bar because of this much expansion or because of rise in temperature delta T. So we have got what is the force developed in the bar or what is the force applied by the support on the bar. Now the force developed is a compressive force. So once P is known, so you can easily calculate the stress developed at right end and the left end. So stress developed at the right end of the bar is given by P by the area, cross-sectional area. Small d is the diameter at this end. So we can write pi by 4 into small d square. So this is the stress developed at the right end, and stress developed at the left end is given by P by pi by 4 into capital D square. So it is seen this capital D is larger than that of the small d, hence this stress will be more than this stress. So we can write the maximum stress developed in this taper bar will be at the right end and is given by P by pi by 4 into D square. And the stress developed at the left end, that will be the minimum stress, and it is given by P by pi by 4 into capital D square. Okay, this is all about the thermal stress strain. Okay friend, so we'll meet soon with the next video. Okay, thank you all. That's all for today's session. We would continue further on this topic in the next session. Keep being connected with us and ask any question in the comment section. Like, share, subscribe, and don't forget to press the bell icon to get notified for future videos. Thank you and see you soon.